Hello, this is Mrs. Ward, and I'm going to go over the notes for section 10.8 and 10.9, graphs of polar equations and polar equations of conics. So what we're going to do in section 10.8 is we're going to graph polar equations by plotting points. We're going to use symmetry to sketch the graphs of polar equations, using zeros and maximum R values to sketch the graphs of polar equations, and then we're going to recognize special polar graphs. So when I start, I'm going to start just like I started in Algebra 1. I'm going to give you an equation. So in this case, my equation is going to be r is equal to -4 sine theta. And in place of sine, I'm going to put these different values. And I picked values from my unit circle so I can do this quickly without a calculator. And what I'm going to do is I am going to substitute in each one. So here I'm going to say r is equal to -4 sine, and then in place of sine, I'm going to put in 0. Well, the sine of 0 is 0, so this will be 0. Then I'm going to do r is equal to -4 times the sine of pi over 6. Well, the sine of pi over 6 is 1/2 times -4 would be -2. I'm going to keep on doing that. So when I get to 2 pi over 3, or when I get to pi over 3, the sine is square root of 3 over 2. Multiply that by 4. I'm going to get -2 times the square root of 3. The sine of 1/2 is 1, so this will be -4. -2, I'm going to keep on filling these values out. So I fill those values out, and now I'm going to go here and I am going to sketch my polar equation. So first one I have 0, 0, so I'm just going to plot a point at the pole. Then at pi over 6, so here's my pi over 6 line. Here's my pi over 3 line, pi over 2. At pi over 6, I'm sketching -2. So this direction is positive, but I want to go negative, so I'm going to go 1, 2, and I'm going to plot that point right there. Then I'm going to do pi over 3, -2 times the square root of 3. I figured out a decimal approximation for that, which was 3.5. So that'll be -3.5. So here's the line pi over 3. I'm doing negative, so I'm jumping the pole 1, 2, 3.5. And then at pi over 2, here's pi over 2, but it's negative. So my r is negative, so I'm jumping the pole 1, 2, 3, 4, and I'm plotting that right there. Then I'm going to do 5 pi over 6, or I'm sorry, 2 pi over 3, and that's -3.15. So 1, 2, 3.5. Then I'm doing 5 pi over 6, which is here, negative, hopping the pole, 1, 2. And then I'm doing pi, which is 0. And then 3 pi over 2, which is this angle down here, and it wants 4, which I see that I'm going to start mapping on the same places, because when I do 11 pi over 6, here's 11 pi over 6, it wants 2. And when I sketch this graph, it looks like it's going to be a circle that's below the pole. So there are some tricks to make this easier. So when I talk about symmetry, so when symmetrical, it means it looks the same. So like if I'm symmetrical, the line of theta is equal to pi over 2. Here's this line, theta is equal to pi over 2. That means the left side looks like the right side. When I say it's symmetrical with the polar axis, remember this is the polar axis, what we used to call the x-axis. And if it's symmetrical to this, that means the top half of the graph looks like the bottom half of the graph. And then you have symmetrical with the respect to the pole, which means it's symmetrical over both. So it's like you take this point, you fold it down here, you fold it over here, and you get the same point. So these are the different ways that you're going to be symmetrical. And what I'm going to tell you is that if I'm symmetrical over the line theta is equal to pi over 2, I can replace r theta with r and then pi minus theta. Or I can just, the easiest one is take this and then change both the r and the theta. If I'm reflective over the polar axis, I'm going to take r theta, and the easiest one is just to keep the r the same and make it negative theta. And then the pole will replace r theta with, probably the easiest one is negative r theta. So what you're usually going to do is when I see the graph of sine, anything that has a sine in it is going to be symmetrical with the line theta is equal to pi over 2. Anything with cosine in it is going to be symmetrical with the line of the polar axis. So what that means is that if I have sine in there, that means when I go the graph at the left and the right sides will look the same. If I'm graphing a cosine function, that means the top and the bottom will look the same. So when I'm going to graph points, if I know that I have a sine curve, I'm only going to pick values from the first and the fourth quadrant. So I'm only going to pick values from here and here, knowing that I can map them over to here and here because it's symmetrical. When it comes to cosine, when I go to pick values to substitute in my table, I'm only going to pick values from the first and the second because to get the third and the fourth quadrants, I'm just going to map those points down because they are symmetrical. So here I have a graph of r is equal to 3 minus 2 cosine theta. It's telling me to use symmetry to graph this. When I go to make my points, what I'm going to do is I'm going to do my table vertically this time. I'm going to do r and theta. So when I pick theta, I'm only going to pick theta from the first and the second quadrant. So I'm going to start with 0, and then let's stick with pi over 6, pi over 3, pi over 2, and then keep on going. So 2 pi over 3, 5 pi over 6, and then finally pi. Those are the values that I'm going to pick. And since I know my unit circle, this will go rather fast. So when I go up here, I'm going to do 3 minus 2 times the cosine of 0. Well, the cosine of 0 is 1, so this will be 3 minus 2, which is 1. When I do 3 minus 2 times the cosine of pi over 6, the cosine of pi over 6 is the square root of 3 over 2. Multiply that by 2. So this will end up being 3 minus the square root of 3. When I go to do pi over 3, that's 3 minus 2 times the cosine of pi over 3. Well, the cosine of pi over 3 is 1/2. It's 1, which is 2. When I do 3 minus 2 times the cosine of pi over 2, cosine of pi over 2 is 0, so it's 3 minus 0, which is 3. Now, let me just show you this. So 0, 1, I'm going to plot the angle 0, the radius is 1, so I'm going to plot my point right there. Now my radius is pi over 6, and then 3 minus the square root of 3. And I'm finding a decimal approximation for that, which is going to be approximately 1.3-ish. So I'm at pi over 6. I'm doing 1.3, so I'm going to put a dot right about there. Then I'm going to do pi over 3, 2. Pi over 3, 2, so right there. And then pi over 2, 3. 1, 2, 3. So I have those points there. Now I'm going to use the fact that it's symmetrical with the, and I'll do the other half in a second. I'm going to do symmetrical with the polar axis. So here's the, because it's cosine, so here's this polar axis, and I'm just going to map the points down. So what I'm going to do is I'm going to, this point can't be mapped because it's on that line, which I drew really bad. So let me just bump that line up. There you go. And now I'm going to, so when I'm at pi over 6, I'm going to go here. Whoopsie, should be a pen. Here, and then when I do pi over 3 there, and then pi over 2 will be 3, so there. Now I'm going to keep on drawing my points. So at 2 pi over 3, this will be 3 minus 2 times the cosine of 2 pi over 3. The cosine of 2 pi over 3 is negative 1/2, so this will be 3 plus 2, or 3 plus 1, so this will be 4. And then this will be 3 minus 2 times the cosine of 5 pi over 6. The cosine of pi over 6 is a negative square root of 3 over 2. So this will be plus the square root of 3. And then pi will be 3 minus 2 times the cosine of pi. The cosine of pi is a negative 1. So negative 2 times negative 1 is a positive 2. So this will be 5. And when I go to plot these points, I'm going to do 2 pi over 3, 4. So 1, 2, 3, 4. Then I'm going to do 5 pi over 3, and then it's 3 plus the square root of 3, which a decimal approximation for that is going to be 4.7. So oh, that's off the graph, so sorry. And then pi will be 5, so that'll be here. Again, mapping down, can't map this one because it's on that line. Mapping, and then mapping down. And then I'm going to have a shape that looks like this. It's called a lemicon. And it's just going to be kind of like a circle, but it's going to have that little divot. So when I look at this graph, I want to point out some things. First of all, if I ask you, looking at these graphs and even looking at this picture, the graph, I have a maximum value and I have a minimum value. The maximum value, or the farthest I get away from the pole, is going to be this point here, which happens at pi. The closest I get to the pole, you know, the pole is here, the closest I get to that is right here at 0. So my max of my function is going to be 5. The minimum of my function is going to be 1. These are going to happen when my cosine is either at its max or my min. And if I just think of just cosine by itself, when you were in trig and you thought of like cosine x, you knew that when I did this, when I found the value of cosine x, it had to fluctuate between -1 and +1. That's going to be this one would be the max, this negative would be the min. That's going to be where my max and my min occur, is going to be when my cosine is equal to 1 or cosine is equal to -1. It works the same way for sine. I don't know which one's which because, see, this one I had the negative sign in front of it. So like what normally was my min, because the cosine is equal to -1 when x is equal to pi, and this happens when x is equal to 0, they switch places because of the negative sign. So normally my cosine is at its min when the cosine is equal to -1, which happens when my angle is pi. But since of that negative sign, that pi now becomes my max. We'll go into that a little bit more. So when I go to, let's go to another one, that this one I'm going to use my max and my mins and my zeros to sketch a graph. So it, like in regular math and regular points, we tend to use the zeros a lot to graph. But the problem with zeros and polar is that the 0 is going to be here. So if I have an angle of 0 degrees, I'm going to be at the pole. So that really doesn't help identify the shape of my graph at all, because it's just going to be a dot at the pole. But I'm still going to identify where those zeros take place. In other words, at what angle I have a 0. Then my max and my min R values, those are going to be key, especially when I go to sketch my rose curve. So this one, it wants me to, so let's find the zeros. To find the zeros, you're going to set 0 equal for R, because you want your radius to be 0. 1 plus sine theta. And then I'm going to have -1 is equal to 2 sine theta. -1/2 is equal to the sine of theta. And then I have to ask myself, when is the sine equal to 1/2? A -1/2. And that normally happens at 7 pi over 6, knowing my unit circle, and 11 pi over 6. So my zeros are going to be 0, 7 pi over 6, and 0, 11 pi over 6. And you're going to have to be able to identify your zeros. So you set the equation equal to 0, you solve for it, hopefully you know trig, and you're able to find those values. Now to find the max and the min, you're going to say, well, the most that sine theta can be is 1. And the least that sine theta can be is -1. So you're going to put those in place of this sign. So R is equal to 1 plus 2 times 1, which will be 3. And then R is equal to 1 plus 2 times -1, which is going to be -1. So the max of my function is going to be 3. The min of my function is going to have a radius of -1. To find the angle, I take this sine theta and I ask myself, when is the sine of theta equal to 1? Well, that happens at pi over 2. When is the sine of theta equal to -1? And that happens at 3 pi over 2. So that's going to be the max and that's going to be the min. Now, if I were to plot those, I'm going to 11 pi over 6 plotting 0, going to 7 pi over 6 plotting 0. Again, not helpful at all. Then I have pi over 2, 3, 1, 2, 3. 3 pi over 2, negative 1. So here I'm at 3 pi over 2, but I go to negative 1, so I'm up here. And then I would probably plot more points to figure out what this graph was going to look like. Since it's a sine curve, I know I'm going to pick points from the first and the fourth quadrant to map it over to the left and right because it's going to be reflective over the line theta is equal to pi over 2. So the points that I have aren't helping me because they're on that line. So I'm going to pause this video, set up a graph, and graph the rest of those points. You should be doing the same thing too, by the way. So I made up a table, and this is the table that I made up. I picked points from the first quadrant. I picked points from the fourth quadrant. And I didn't pick the ones that I already used, but I forgot that I picked 11 pi over 6, and I did get 0, so good for me. So I plotted these points here. So I plotted 0, 1, and now I'm going to map it over, so I'll have this point here. I plotted pi over 6, and that was 2, so I'm going to go over here, 2. This was 2.7, so 2.7. And I think that's all I can do. Oh, and then I did have 5 pi over 3, which is negative 0.7. So here's 5 pi over 3. Down here it is negative 0.7, which will map over here. And when I sketch my graph, I get something that looks like this. Now let's talk about using your calculator to do this. So if I do my calculator, I'm going to add a graph. Right now it's a function. I'm going to hit menu, graph entry edit, and you will see that there is a selection for polar. I'm going to type in the polar equation, which was 1 plus 2 sine, and then you see how there's a theta here by that R1, you have to put in theta. I usually get that by pressing the pi key, and then there's theta right there. And I'm going to hit enter, and I don't know why I put a degree symbol in there, hit enter again, and I have that shape right there. All right, moving on to the next one. So here's all the different curves that you did. So what we just did is a lemicon. Those are the ones that we just did, and they either have the little, or they have a little divot, or you want to word it, and then circles, and then we're going to talk about the rose curves. And I love the rose curves because they're pretty, but I also like the rose curves because they're a great way for me to test whether or not you can find a max and where that max occurs. So the only one that you're going to be expected to graph besides graphing points is as to and without checking your calculator is a rose curve. So I have these rose curves, so I'm focusing on these. And when a rose curve always comes in a pattern of R is equal to A, and then you either have sine or cosine. So let's say it's cosine n theta. This A is going to be your max or your min, depending on if it's positive or negative. This n tells you how many petals you have. And if n is odd, that's the number of petals you have. If n is even, then you have twice as many petals. So let's just do one. So that's the blown up. Okay, so here I have R is equal to 4 cosine 2 theta. So my max is going to be 4. And I know it's a max because it's positive, so it's going to be 4. This 2 theta tells me my n is equal to 2, which tells me that I am going to have 4 petals. Now, sine and cosine, and it only happens with sine and cosine that you have this rose curve, is going to be symmetrical. Since it's symmetrical, either the top and the bottom have to look alike or the left and the right have to look alike. Either way, that means that these petals have to be evenly spaced. So I like to figure out how far between my petals I'm going to have, between the tips of the petal. So 2 ways you can do it. A whole lap around the unit circle is 2 pi, so I can take 2 pi and divide it by 4 and get pi over 2. So there's going to be pi over 2 spacing between. I'm not saying that that top of that petal happens at pi over 2. I'm just saying that there's pi over 2 between. Or if you're not a big radians fan, you take 360 degrees divided by 4 and you realize that you're going to have 90 degrees between each petal. So if you had a petal, say like here at 30 degrees, then your next petal will be at 120 and then 210 and so on and so forth. But you only have 4, so I could have kept on going, but I didn't. All right, so my max and my min are going to happen when the cosine, I'm going to write x, purposely not writing theta, is cosine is equal to 1, cosine of x is equal to negative 1. Those are the 2 places where my max and min will occur. So what I'm going to do is I'm going to ask myself, when does the cosine of x normally equal 1? Well, that normally happens when x is equal to 0 or problem is I don't have x. I don't have x. I have 2 theta. So when in place of this x, I am going to write what I said it was, which was 2 theta. So I'm going to say 2 theta is equal to this 0. And I wrote 2, so 2 theta is equal to 2 pi, because the more you can get, the better. Divide both by 2, and I'm going to have 0 for this one and pi for this one. So this is going to be max because 4 times the cosine of 1 will be 4. So my max, my radius will be 4, and that happens at 0, and that happens at pi. Let's go ahead and do the min. The min, same thing. I have cosine of x is equal to -1. That usually happens when x is equal to pi, but I don't have x. I have the 2 theta, so I'm going to say 2 theta is equal to pi, which means theta is equal to pi over 2. So my min is going to be -4, because this whole thing will be -1 times 4, -4, and this is going to be pi over 2. So I have 3 out of the 4, so I'm pretty lucky on this one. So 4, 0, 1, 2, 3, 4, plot a dot. Reflective over the polar axis, that does me absolutely no good because it is on the polar axis. 4 pi, so I'm going to go out to pi, plot the point 4, and then pi over 2, and my radius is -4, so I'm going to jump the pole and go down here. But it's reflective top bottom, so then I can map this one up here. I have 4 petals, I have 4 dots. It's a lucky, lucky day, so I'm going to sketch my 4 petals. I don't care how wide you make those petals, how skinny you make those petals. I'm looking for if you place the max in the right spot and if you knew what the maximum was. Let's do one more. So here I have r is equal to 2 sine 3 theta. So this 2, since it's positive, is going to be my max. 3 theta, my n is going to be 3. So if n is equal to 3, that is an odd number. So that means I'm going to have 3 petals. If I want to figure out how far apart they are, I'm going to take 2 pi and divide it by 3. Can't really do anything with that. 360 degrees divided by 3, and I see that I'm going to have 120 degrees between the petals, or 2 pi over 3 radians. The most that this is going to be is when the sine of 3x is equal to 1. So we did say my max was 2. That's going to happen when the sine of x is equal to 1. So that the sine of x is equal to 1 when x is equal to pi over 2. So now I put in that 3 theta. So 3 theta is equal to pi over 2. Divide by 3, multiply by 1/3 would be more convenient. So I'm going to say theta is equal to pi over 6. So pi over 6, I'm going to have a max of 2. So that's my max. To find my min, I say when is the sine of x equal to -1? That happens when x is equal to 3 pi over 2. So then I say 3 theta is equal to 3 pi over 2. So divide by 3 or multiply by 1/3, and I'm going to get theta is equal to pi over 2. So then I'm going to have -2 would be the r, and then I'm going to have pi over 2. So when I plot these first points, the first point is pi over 6, 2, pi over 6, 2. This is theta, so it reflects, this is sine, so this reflects over the line. Theta is equal to pi over 2. So I'm going to sketch that, reflect that point, and I'm going to have the point right over here. And you should notice that that goes from pi over 6 to 5 pi over 6, or from 30 to 150, which happens to be 120 degrees apart. Then I'm going to do the min, which is pi over 2. So up here, plot the radius -2, so I hop the pole -2. I need 3 petals. I have 3 dots, so I'm good to go and sketch my petals. And that's how I do that rose curve. Now I'm going to move on to polar equations of conics. So when we go into this one, we're supposed to use eccentricity to write and graph a polar equation. We're not going to do that. And we're going to use equations of conics to model real life. Probably not going to do that either. Well, we're not. So here's what you're doing. Remember eccentricity from when we did ellipses and we talked about the eccentricity where we did the A over C. So this is saying, like, if I have the eccentricity and I wanted to find out what type of equation I have, I'm going to write the equation as r is equal to my eccentricity times my p, and I'm going to put that over 1 plus or minus e times the cosine of theta. When I look at these equations, the most important part is that these have to be 1. And then if the eccentricity has to be greater than 0, and then you're going to be able to identify the graphs. What we're going to use this for is we're going to take an equation and we are going to rewrite it into standard form so that we're taking it from polar, and eventually we're going to go from polar to parametric to rectangular. But when we start this one, so let's just start with this one. I have r is equal to 15 over 3 minus 2 cosine theta. If I wanted to change this to rectangular, in other words, I want to get rid of the theta and the r, and I want to rewrite it in terms of x and y, first thing I'm going to do is get rid of this denominator. So I'm going to multiply both sides by 3 minus 2 cosine theta. So I'm going to have r times 3 minus 2 cosine theta. That's going to equal 15 because these will simplify. And when I distribute the r, I'm going to have 3r minus 2r cosine theta is equal to 15. As soon as I see this r cosine theta, I am going to make that x. So I'm going to have 3r minus 2x is equal to 15. Then in order to solve for, to get rid of the r, it either has to be squared or has to be times the trig function. So I'm not going to be able to multiply times the trig function, but if I isolate it on one side by itself, I will be able to square it. So I'm going to say 3r is equal to 2x plus 15. I added 2x to both sides. I'm going to leave the 3 here, and I'm going to square both sides. Doesn't matter. So I'm going to have 9r squared is equal to, and then I have to FOIL, so this will be 4x squared plus 60x plus 225. Then I'm going to divide by 9. Yeah, sure. And I'm going to leave it like that for a second. So I'm going to have r squared is equal to 4x squared plus 60x plus 225 over 9. R squared I can rewrite as x squared plus y squared is equal to 4x squared plus 60x plus 225 over 9. Now I'm going to decide that I didn't want to multiply both sides by 9, so I'm going to divide both sides by 9, so now I'm going to multiply it. So I'm going to have 9x squared plus 9y squared equal to 4x squared plus 60x plus 225. So I do recognize that it's going to be one of my conics. To do that, I'm going to have to set it equal to 1. So I'm going to bring everything from this side over, except for I'm going to leave this here because I'm going to end up completing the square. So when I subtract 4x squared, I'm going to have 5x squared minus 60x plus 9y squared is equal to 225. Then I'm going to complete the square like I did before. Here I'm going to factor out my 5 and make this 5 times the quantity of x squared minus 12x. I'm going to leave the plus, leave a space. Plus 9y squared is equal to 225. To complete the square, I take half of 12, which is 6. 6 squared is 36. 5 times 30, well, now when I added that 36, I really added 5 times 36. And when I do that, I really added 180 here, which means I'm going to add 180 to this side. So 225 plus 180 is going to be 405. Conic, want to set it equal to 0, so I'm going to divide both sides by 405. So I'm just showing that I'm dividing everything by 405. So I'm going to have x minus 6 squared over 81 plus y squared over 45 is equal to 1. So here, since I have both of the variables are positive, I realize that I have an ellipse. I realize that the center of the ellipse is 6, 0. I realize that if I wanted to do the vertices, the major vertices, where I add the square root of 81 or I add 9 to the x, I'm going to have 15, 0, and negative 3, 0. And my minor vertices is going to be adding the square root of 45. So 6 and then plus or minus square root of 45 would be 3 times the square root of 5. and that's it. That's all I have to do. So I took a polar equation and rewrote it into rectangular. By putting it into rectangular, I can identify the shape as an ellipse.